So now we will start our derivation for Maxwell-Boltzmann law of distribution of molecular velocities. So according to kinetic theory of gases, we know that the gas molecules are constantly moving in every possible direction and their velocities can range from 0 to infinity. So Maxwell in the year of 1859 first derived the law which showed that the velocities are distributed, how the velocities are distributed among the gas molecules statistically. Okay. Then in the year of 1879, Boltzmann did the rigorous proof of this distribution law given by Maxwell, and he generalized the law to express the distribution of energies among the gas molecules. The same law can be used also to show the distribution of momentum among the gas molecules. Now, before deriving this Maxwell-Boltzmann law, we need to make some assumptions. Okay. Now this law is based on assumptions of the kinetic theory of gases, plus there will be some additional assumptions. And all these assumptions are made for ideal gas. So the law is mainly applicable for ideal gas. So the first assumption is that when there is no net force acting on a gaseous system, there is no mass movement or convection current within this gaseous system. It means that if there is a force acting on a gaseous system, then the molecules will be particularly moving parallel to the or in the direction of this force. Okay, so there will be a mass movement, or there will be gas molecules moving from one region to another region as a whole. We know that the gas molecules are individually moving in different direction, and there is no particular direction or preferred direction. But if there is a net force, then there will be a preferred direction in the movement of the gas molecules. But when there is no net force, there will be no preferred direction in the movement of the gas molecules, so there will be no mass movement or convection current. Then the second assumption is that the x component of velocity of a gas molecules is independent of y or z component of velocity of that gas molecule. It means that if we know, the gas molecules are moving in 3 dimensions. So its velocity can have 3 components, x, y and z. Now if we know the x component velocity of a gas, if we know the value of x component of velocity of a gas molecules, in no way can we tell that what will be the values of y component or z component of velocity of that particular molecules. Okay. Or similarly, if we know the value of y component, we cannot say what will be the value of x component or z component of velocity. Or if we know the z component of value of z component of velocity, then we cannot say what will be the value of x component or y component of velocity of that gas molecule. Next, the third assumption is that probability that a random gas molecule has velocity in a certain range depends on 2 factors. The first one is the distribution function at that velocity, and the second one is the range or interval of that velocity. So we said earlier that to derive this velocity distribution law, we need to know about the velocities of the gas molecule constituting the system. So to do that, what you have to do, we start with randomly selecting any gas molecule and measure its velocity. Okay, measure its exact velocity, but we cannot really measure that what will be its exact velocity. Instead, we give a probable idea. Okay, so we measure the velocity probabilistically. Okay, so we measure velocity probabilistically. That is, we say that generally what should be done, that is, we select a random gas molecules and measure what is its exact velocity, but we cannot do that. We cannot see a gas molecule moving and we cannot measure in 1 second how much distance is covered. So what we can say, we can just say that okay, it is probable that the gas molecule has a velocity. We do not give the exact velocity, we say that the gas molecule has a velocity lying in a range, in some range. Okay, and we cannot be sure that this gas molecule has this exact velocity. We can say that it is probable that the gas molecule has a velocity lying in some range. Suppose the gas molecule has a velocity lying between c and c plus dc, and we measured that probability. That probability will give us an idea of that velocity. Okay, so if you remember this example that we discussed earlier, that suppose there are n gas molecules. Out of n gas molecules, there are dn molecules which have their velocity lying between c and c plus dc. Then what will be the probability that if we select a random gas molecule out of this slot, out of this dn number of molecules, that they will have their velocity lying in this range c and c plus dc. And we found that that probability was dn by n, and it was equals to fc dc. So this is the measurement of that probability that the randomly selected gas molecule has a velocity lying in this range. So this is how we measure the velocity of a gas molecule in probabilistically. Okay, so see, this probability is a product of fc and dc. fc is the distribution function at that particular velocity c, and dc is that interval, velocity interval or velocity range. So it depends on the probability, depends on two factors. First, the distribution function, and second, the interval. Okay, so here you see the probability depends on two factors. First, the distribution function at that velocity fc, and the range of or the interval of the velocity, which is dc. Then the last one is that we consider that the gas molecules are only moving with translational energy. They don't have any vibrational or rotational energy.